All right, well, welcome everyone to the Berkeley seminar. We're very happy to have Benjamin Brast McKie talk about some temporal logic. So thank you, take it away.
Yeah, thanks so much for having me. It's great to be back. This paper is about tense and modality. Specifically, I'd be interested in a kind of historical modality, so like quantifying over different histories that a system may follow. And I wanted to just start by giving a little bit of context for the broader project, since this is a fragment of it, where I've been working on developing a language and trying to implement the semantics and proof theory for this language using the model checker, which is a package I developed for implementing semantic clauses using Z3 in order to find countermodels. And then also implementing the proof theory inside Lean. And the goal here is to provide RL signals in order to train an AI to be able to reason in this language. And the primary application I have is planning. And so this paper focuses, if you think about our plans and the way they go, okay, we're at a point here. And what we think about is some kind of, the future contingency, the different ways things could go. And so this is a kind of, where, okay, here's the past, which we may or may not know in full detail. And so what this paper focuses on is just our ability to quantify over these different possible histories, and then inside each of them, scroll forward or backwards in time using tense operators. I should say there's the other natural operators that I care about, but won't focus on here, counterfactual operators, where very often we think, oh gosh, if only, we look back in time, and then we think if things had been a little different, we think about some counterfactual, and there's some other points here, and we think about how those points might evolve. So this is the kind of application that I have in mind, where we use all of these parts in conjunction. Human beings, that is, use all these operators in conjunction in order to interrogate our plans, make sure they're good plans. Even if you have a great history, if it follows its natural course and all goes well, if there's some potential fail points, which have bad outcomes, that can sink a plan. It can make it not such a good plan. And so this is the application that I have in mind. In order to try to promote trustworthy forms of AI reasoning. Okay.
You also build in the order of time?
Yes. So
it will be in the future or something like that.
Say that again?
5x, if 5x holds now, will it also hold in the future? I mean, to have some ordering?
Yes. So
just always and sometimes doesn't have any ordering.
Yes, that's true. So I'm trying to define, or I'm defining these in terms of, so this is always in the past, and then this one will be always in the future.
Yes. Okay.
Exactly, yeah. Okay, yeah, let me say something about these. So as I've been trying to build up this language with lots of different operators in them, not only do you have to explore the logics for each of those operators, but also all their interactions. And this is often, and this promotes change inside the semantics. And so these principles, perpetuity, is a natural example of the kind of interactions that don't always work out when you take just the simple combination of one framework and another. So this reads, if it is necessary that phi, then it's always the case that phi, or it's dual. If it's sometimes the case that phi, then it's possible that phi. I think these are good principles, and that if we don't have them, something has gone wrong. Our semantics is not capturing, if they come out invalid, our semantics is not capturing what it should capture. We're not really describing the operators that at least I'm interested in. And so I wanted to, in order to kind of motivate where I end up in the system that I build, I wanted to follow a little piece of the history. Since looking back into the past, looking at both Pryor and Kaplan's semantics, they provide a nice motivation for the move that I make. And the move that I make, I think in some ways is small and well anticipated in physics. And it draws a direct link between a bimodal logic with both tense and modal operators and dynamical systems theory, which we've been exploring in some ways since the scientific revolution. So a very old way of thinking about evolving systems and connecting that to reasoning inside an object language with tense and modal operators. So that's my plan. I encourage you, if you have any questions, please interrupt me. Yeah.
I have a question then.
Yeah.
So do we ever stack these operators with each other? So could you say something like it was always possible that phi?
Yeah. Yeah.
Like that would be something
Always.
like past operator diamond. Yeah.
So yeah, or if you want to say just of the past.
Yeah.
Yeah. It was always possible that phi. Yes. Yes.
Okay,
You can
so it stacks in that order. So like it's for
Or-
the entire path. It's possible that phi.
Yeah. Or I mean.
There's a distinction to be drawn here between it's possible that phi was always true.
Right.
And in the past, it was always possible for phi to be true.
Yeah, so you could like change the order. Yeah, absolutely. Yeah, and then what kind of, what our logic will ultimately say about like, how these all stack, which ones can you change their order and so on. Yeah, that's what the logic should answer all of those questions.
A little about, always in the past, it was possible that phi, but does it mean in the past it was possible?
In the past,
See, always in the past,
yeah,
it was possible that phi,
yeah.
but it doesn't mean that it was possible in the past. Does
Yeah, I mean, well, I should give you the semantics before we tried. Yeah, like, so one thing about this I should say is the kind of systems I want to be able to study. I want to be very general. I don't want to have to put constraints. So we often think for ourselves that time is infinite in the past. I mean, I don't know. It seems reasonable enough. But for many systems you might want to study, say like a chess game, it's not like that. There's a first move. And so if we happen to be standing at that first time, and you say always in the past phi, well then trivially, because there are no past times, this will hold. So there's certain things to watch out for. Of course, if you want to restrict to a certain type of system that has an infinite past in the time, then yeah, you can strengthen the logic in certain ways. Okay, well, let me try to build up the semantics for you. I want to say something about Pryor's semantics that he explored. And really, I'm going to be focusing on Thompson's reconstruction of it. And the kind of picture looks a little bit like this that I've drawn here. And so we start off with T, and we have some order. He uses a strict partial order, so I'll just continue with that. And I'm just going to be doing propositional logic here. So some interpretation function where you have pi is a subset of T, so all the times in which pi is true for all pi inside our set of sentence letters. Okay, so we have some model like that. And then, okay, what does this give us? We have, so because we have this strict partial order, he then builds out of it histories, which are the maximal total suborders. So, imagine you have some tree like this, and any sort of branch of that tree will be inside. So use like h sub I is inside h of p. So these are like all the histories, all the branches of our tree. And then he uses these in order to to do something, not so far from what I had in mind, where you're imagining future contingency, the future is open, there's many different branches, and then you can evaluate the sentences of your language by saying, first, which sentence letters are true in which histories at which times, and then recursively, for all the other operators, you can say, in a given history, at a given time. So we specify both. Give myself a little bit of space. So we'll have our model, I'm calling it P. We have some history HI, and we have some X. And so at a given time, inside some history, you can ask, was it always the case that phi? Or will it always be the case that phi with the F? Okay, so this is a kind of good start. And all the way back, and yeah.
So 3 quick questions.
Mm-hmm.
The simplest one first, what's going on in number 9 there? What's our dot in the box operator?
Yeah, okay, good. So this, Prior is very clear that he doesn't read this as this like full strength necessity quantifying over all histories. And the reason for that is because let's say we have some other, I need some other colors here. Let's say we have a history here, some other path, some other branch of our tree, and it has incomparable times, just times that don't occur in this history. Well, there's just no good way for me to interpret. Let's say we were at X, and let's say this is HJ. It just doesn't make any sense at all to try to evaluate anything here. This just doesn't work. And so what he gives us instead is this stability operator, where he reads stably phi, meaning for all the branches that intersect this point, then phi holds. And that is still useful. Useful because we can say things like, we can define, if it's stably, say, always phi, what does that mean? Well, it's like, say I'm at this point, meaning you look at all the different intersecting branches that may from this point. Well, in all of the future points from there, phi is the case. That often is the kind of thing we want to say. If I say like, there will be a sea battle tomorrow, I don't really care about the other incomparable branches, which don't intersect with me. I'm talking from this point, going forward, all the different ways that things may branch going forward, there's guaranteed to be a sea battle tomorrow. We might, in that case, since it's not, we would do it something like this. There's some future time where, say, the sea battle happens. Okay, so that's what he gives us. And there is still some kind of restriction here. So this is a weaker modal than something that quantifies over all histories. And there's not really a good way around that. So he doesn't try to give us more than that.
Other short questions ahead, sorry.
Oh, yeah, sure.
So, second thing, when you say the interpretation of a sentence letter PI in Blackboard L,
Yeah.
what does that mean? Is it just like saying when in time, when in this branching time model, PI is true, or something else?
Yeah, excellent. So this is just what I wanted to move to, which is you can ask, what does this really mean? I think in modal logic, say when we're thinking about worlds as, say, just situations or something circumstantial, some like complete configuration of a system, well then what this ends up being is all the different configurations of that system. So let's, just to take a simple example, say a chess game, say like white is in check. Well, there's many ways for white to be in check, and what we'd have to assign here would be the set of all the configurations of that. Okay, that's not really what's going on here. Instead, what we have are, what we're told is when white is in check, right? And this is also a major limitation of this framework. And I think to bring it out, I mean, chess is a very nice example because so often what you'll end up with is some meandering end game, right? Where, okay, we end up in a certain board state and we play on, and then lo and behold, we end up back in that same board state again. So the way that our, if you imagine, there's like a little loop-de-loop where somehow we ended up in the same state more than once. Okay, very common. Or in chess, you also have transpositions where, okay, you go this way, but you might actually also go this way. There's two different ways to end up in the same board state. Different move orders, but lo and behold, we end up in the same place. Okay, this is forbidden inside this picture, just given how this thing works. Right? You can't have a time be before itself. That makes no sense. And if we give up the idea that this is a strict order, if it's no longer like that, if we give up transitivity, if we give up irreflexivity, I mean, we just kind of lose our grip on what this was meant to be, which is this earlier than relation, relating times. Okay, so I think this kind of indicates that, though we're targeting something, I think, very natural here, it's actually more natural to actually be thinking about the world states themselves. And this kind of shows up in Prior himself, where, okay, officially he calls T a set of times, but actually when he goes on talking about them, he often calls them moments. Okay, maybe those are just the same as times, but he also calls them world states. World states to me feels a lot more like configuration, but that's not really a fair interpretation of what this is. What we're really told, the truth conditions for the language, it's really when a sentence is true, not what state it's in. Yeah?
And how is it not a configuration if at any element of T I can look at what subset of L obtains for that moment of T? So how is that not a configuration at that time?
So yeah, like say, I don't know, P1 is white is in check. And we could look at all the different times at which, over this whole tree, in which white is in check. But maybe some of those times at which white is in check happen to be the same board state, and other ones are novel. There's no way to kind of extract that from what we're told. We're just told white is in check. That's all we know. It's true that if you had a very descriptive language with lots and lots of predicates and so on, that maybe you could, like you'd have other sentences like rook is on e4, and you'd have enough in order to kind of recreate what the board game, or what is going on in that game to be able to differentiate. But just given a sort of simple propositional language where these represent atomic sentences, that, yeah, I guess the distinction is knowing when something is true is different than knowing what the state of that system is.
I could have two different elements of T that have the exact same set of subset of L true at it.
Yeah, and that's yeah, exactly, and that's what's going on right here. It's kind of like this is meant to be the same board state, and yet it happened at different times, right? We've kind of looped back around, and that should.
I was like, that's not representable.
That's right.
Like, maybe it's like this represents world states, but it has some constraints on. Anyway, I think I understand that.
Yeah, exactly. Okay, so if we care about trying to capture that, I think one other sort of proposal that has gained some currency, especially inside linguistics, following Montague and Kaplan, this is Kaplan's version of it, is this two-dimensional semantics. So you think, okay, just helping ourselves to times themselves is kind of not enough. We need more than that. And so instead we're going to have worlds and times, and we'll still have, I'm going to use just to kind of follow, they use a partial order, a weak partial order instead of strict. Okay, so now we think, well, how are we going to interpret these? Well, W can't, it's not that natural to think of W as world states themselves. And the reason is if we're going to interpret sentences now at pairs, so M2, say WX, well, if this is a world state, that should kind of already be quite enough, at least to figure out if this is true. And then X is a time. They're kind of competing. If they're both instantaneous kind of things, they're competing for the same theoretical role. It's not really what we want. So instead, the picture in two-dimensional semantics that we get, I guess I'll erase this for now, is where, okay, you have these different worlds. Here's W prime, and so on, many of them. And then you have the different times in all of those worlds. And then what a proposition is, say PI is going to be a subset of W cross T. So it's going to be some, I don't know, maybe it includes just these. Here's one proposition that you might express. So it's true in these worlds at these times, I don't know, this is X, Y, here's X, Y, and so on. Okay, so I think in some sense that, this picture it's just the cross product of our tense logic that we had before with, in this case, it's an S5 modal logic with no restrictions whatsoever. Neither Montague nor Kaplan use any restriction on which worlds could see which. Every world sees every world, so you just quantify over all of them or none. And this may seem like the simplest way to combine these two pictures, but the problem is neither of these come out as valid. Okay, and why is that? And let's give an example. Let's say there's just these two worlds, none others. Phi happens to be true at both of them at time x, but not phi happens to be true over here. Okay, well now consider this. Okay, so the problem is when we're evaluating phi at, say, Wx, it does come out necessary, that phi. Why? Well, because as we change W between W and W prime, phi remains true. But it's temporary. It's as temporary as can be. It's only true at x. So if we change this, so even though phi is necessary, it's not always the case. That seems to me like a disaster. To me, it seems like, okay, we're not really capturing what these operators should mean. Yeah, we've missed something. And so the paper goes through, attempted ways to sort of save this, and I argue that none of them really succeed. The thought being is, you might try a kind of plenitude principle, or I call it abundance, basically, which requires whenever you have a world like this, there has to be another world that's somehow staggered, pushed in one direction or another. And if you require all sort of shifted worlds to exist, then if it's necessary, well, because all the shifted worlds have to exist, well, then that means that it would always have to be the case, because if there were any time where it's not the case, well, we could just shift things over, and then that would be a counterexample. I don't know if that makes sense. But this is, yeah, it sort of feels rather desperate to me. I guess it feels like it should be cooked in and sort of emerge from, it shouldn't be something that, we shouldn't get these principles by some ad hoc constraint added on top. It should rather emerge naturally.
So,
yeah.
Are our times here still partially ordered, or are they not totally ordered? My question is now how this two-dimensional semantics model differs from the branching times model from the previous one, or we can just think of the different branches as being different worlds. We sort of ignore everything before some point and treat everything as parallel.
Yeah, I mean, I think in this kind of picture, it is very natural to think of this as total order. And I think people typically do. You don't necessarily need to do that, but it's like once you help yourself to this extra dimension, and it kind of feels like we didn't need to do that before. Yeah, that to me is the way that most people seem to use this, but it's not to say that degree of freedom disappears. You could still open up.
Do we have what's our total order on the set of worlds? I don't see a natural one.
Yeah, so I agree. Because now they're kind of, and I think this is also brings something out that is unnatural about this picture, is that, well, what have I done here? I've drawn W and W prime as these extended things, these histories, and yet officially they're represented as just points. They're primitive. Well, this feels very unnatural to me. I feel like if they're going to be extended things, they should be defined. They should have some structure. In particular, they should have some temporal structure. And so this is very much what motivates the picture I want to move to, and which aims to fit in with the way things proceed in dynamical systems, where, I mean, let's just imagine, the simplest, kind of physics example that you get of like the car and, its position as a function of time, right? It's like, okay, we have our system. There's the different states it can be in. In this case, we just care about position. And there's the different times it can hold those states. And then what you do is you draw, you have some function which goes from times to world states. And this has to be constrained in some ways by, say, in this example, by the laws of physics. You can't have the car just skipping all over the place, let's assume. But this is the kind of basic setup, is that what the histories are functions. They're not primitive points. And that to me is like the fundamental mistake of the two-dimensional semantics is, and it's kind of, it just results from, when you're just doing Kripke semantics, sure, then W can be a set of points. When you're just doing tense semantics, T can be a set of points. But once you cross them, once you want to have both tense and modality, it kind of stops making sense to do it that way. And that corresponds with changing the way we interpret this from being states, something instantaneous, to being histories, which I think have temporal structure. Okay, so how does this go instead? Well, now W is a set of not histories, but of world states, of total configurations of the system in question. And then I'm going to help myself to some times or durations, and I want them to have some minimal amount of structure. I want them to be ordered, and I want them to form an abelian group because I want to be able to add them and subtract them. Okay, that's all I need. Okay, and then there is going to be some kind of constraint on them, on their transitions, which states can transition to which. And so I have this arrow here for this task relation, meaning that W transitions to U in X amount of time, or in, duration X. Okay, so those are the basic ingredients. And then we're going to impose these principles. So a frame is such a triple, the world states, durations, and task relation, where, okay, in 0 amount of duration, any world state transitions to itself. Okay, that's just the trivial case. And then they also compose. If I can transition from W to U, and I can transition from U to V, and this takes X amount of time, and this takes Y amount of time, well then I better be able to transition from W to V in X plus Y. And so this is really where my need of additive structure comes from. Okay, and that's it. Very general. I should say that this just is, like, I'm using this 3-place relation here. I'm not supposed to use that board over there. I'm using this 3-place relation here. Another way to do this, instead of would be to have some family of relations for I in D. It's just a change of notation. And this is the way people typically write in dynamical systems theory. And in the case where R, these relations are all functional, then you have a deterministic dynamical system, meaning, W, R, I don't know, say X, U. If R is functional, then we might as well just write it F of W, F sub X of W equals U. Okay, meaning you give me the state W, and you give me a duration time, I can tell you the unique state, U, that you get out. But for non-deterministic systems, there could be many states that you can get to in X amount of time from W. And I just find this a little bit easier to sort of parse for myself, so I've just used the three-place relation instead of the family of relations, if that makes sense. Okay. So that's the basic setup. We still need the elements at which we're going to evaluate sentences, the parameters. And so what we're going to do is define the functions, these like world histories. And yeah, to do that, and this could be relaxed or constrained in different ways, but I'm thinking here of functions being from some subset of durations. And the reason I want that is to accommodate examples like chess, where you might have, all the games have a first time, and some games are longer than others. And so we want to be able to have that kind of flexibility. If you just required all of them to be, every game of chess to begin with the same set of durations, well, that would be quite a constraint. Sure, you could help yourself to null states or something like that in order to exclude them, but yeah, that's what I want. So you have some domain of durations for the history in question. And then the major constraint here is you want that, whatever state you're in at X, that tau y for y greater or equal to X. Okay, so this task constraint, what does that require? Well, it's like, say we have, here's tau. Here's our evolution tau. Here we are at time X. So this is tau of X, some world state. And here's where we are at some time Y. We want to make sure that in their difference in time, that it is possible to get there. And we don't want to just do it for these two times. We want to do it for any two times you choose. And this allows for, it's very general. Time could be continuous, in which case, there's going to be tons and tons of requirements, or time could be discrete, in which case there's just very few. Okay, and this also follows how things go in dynamical systems. These are often called evolutions or trajectories, things like that. And so yeah, the world histories are just the trajectories that are allowed by this task relation. Okay, so now that we have those elements, we can let H sub F be the set of all the trajectories or all the world histories. And then things go as before. I didn't really want to change the semantic clauses too much because I think they're very natural. With the exception of this first one. So whereas before we had, say, Wx, this was inside M2, say Pi, if and only if, we had this, both W, the ordered pair, has to be inside Pi, where Pi is going to be a whole set of ordered pairs. Now we have something, should just be M. Yeah, and then tau x pi. So now what I do is I let tau act on x, tau of x, and I check if that is inside pi. But of course, it has to be defined. So I do also need x to be inside the domain. Say and x in dom tau. Okay. So that's the major difference. The other clauses are more or less the same. You might think, well, okay, this modal here quantifies over all histories whatsoever, so it's very strong. That's true. And if you wanted to have more restricted modalities, you certainly could. And it's kind of easy to define them because now we have so much structure to use. You can define, that set we had before. I think I do this right here. Yeah, this stability. So this is just one example of many. You could say, I want to quantify over all the worlds that happen to agree with the world I'm at, or the world history I'm at the time I'm at. So all the intersecting worlds. Well, we can just do that very easily here. And there's many others. Maybe you don't just want them to agree at that time. You want to agree at all past times. So you could also restrict in that way. Okay, and so this gives you kind of very similar expressive resources with one major difference, which is now these come out valid. And not by some kind of artificial construction, but just very naturally from the way that, from the definitions that we've given. And to see why, let's say, here's some tau that we're at. Let's do, let's do maybe this one. So let's say it's sometimes the case that, say we're here at x, and it's sometimes the case that phi. And what we would really like to get to is that it's possible that phi. Well, why is that true? Well, sometimes phi, that's going to be where either it has been phi, or it is phi, or it will be phi. In the case where it already is phi, of course it follows immediately that phi is possible. Why is that? Well, just from the T axiom. Okay, so that's kind of the uninteresting case where phi already is the case. So the more interesting case is where it's sometimes phi because either in the past or future we have some time where it's phi. So let's imagine we have that sort of scenario. Well, then what we want to get to is we want to get to some sigma where at x it's phi. And we want that because then, given that, it then follows that it's possible that phi at x, because there is some sigma where at x phi. Okay, so how do we get from here to here? Well, it's very easy to define sigma. We can say sigma of x, actually let's do it of z, is just equal to what? Tau of z. And then we're going to do, say, minus x plus y. So we're just pulling it over the right amount. So that, if I plug in x here, sigma x, then what I get out is exactly whatever world state is going to be over here. And similarly for all the other ones. Okay, so the paper shows that just by, a simple induction argument that exactly the same sentences are going to be true here and here, just by the definition of this, the way we've defined sigma. And so that gives us what we want because we know phi is true here. So we know phi is going to be true now at x in sigma. And so that gives us that diamond phi is true here. Okay, and inside physics, I mean, this is kind of as trivial as it gets. It's like, if you have some whatever. You can imagine, I don't know, some path. It's just, and say here's the 0. We're just reparameterizing. We're just saying, oh, no, we're going to move the 0 over here now, right? That's all that's really going on, which I think is good. I think these are true principles, and they should follow from a fairly kind of trivial, it should be cooked in deep into the semantics. It shouldn't sort of be rigged up. It shouldn't require too much jerry-rigging in order to get these to come out as valid. Okay, so that's what the semantics looks like. Yeah.
Is part of the innovation of doing things in terms of durations and not in like some sort of set of times? Is that common or precedented, or?
I feel like in physics there's this kind of doublespeak that goes on where you call them times, but they have their abelian. They're commutative, right? So it's like, it's kind of weird if they named times, like, I don't know, Queen Anne's birthday or something, right? It's like, it's weird to think of those as commutative, right? They're just, so really what they mean is once you give a parameterization, right? Once you have a function telling me where the cart is after 0 duration, after 1 duration, after 2 duration, then you can say in that function, given that function, the time after 2 duration, the time after 3 duration, right? And so this just, times get used kind of instead of explicitly talking about durations. I do feel like in this kind of context, when, I'm trying to be careful about how things kind of evolved conceptually, I think it's worth stressing that they're durations. And in dynamical systems theory, they're also clear that it's a set of durations. So yeah, you can see that as the kind of, as one important innovation. I mean, I don't really want to take responsibility for it. I feel like this is from functional analysis, going back to the, scientific revolution in the way that people are using functions to model the dynamics of systems. But yeah, I do think it's rather the bridge using that kind of dynamical systems theory to interpret a modal language. A bimodal language. Yeah, that's the kind of the only innovation. Yeah.
Sorry, another brief notation question. What does it mean to have a dot inside of a possible diamond? Because I mean, if you want to put it into guess, it's something like is ever true for this history.
Yeah.
Necessarily true to stably true within this history. So if you have something like possible that it's true to is ever true within this history.
Yeah, so say we have some history, and we're at time x, and then I want to say there, stably, dot, I don't know, phi. Okay, what am I doing with this stably? Well, I'm considering all other intersecting paths first, and there may be many. And then I'm saying there's some intersecting path where phi is the case. And so this is kind of useful here. Yeah, this one. So you say could eventually, meaning, okay, we're here. Say it could eventually rain. It's meaning, okay, intersecting with this moment we're in, this history in this at this time, so the state we're in, intersecting with that, there is some future time in one of those histories in which it rains, as opposed to saying something about all of those intersecting histories.
Okay, so we don't care so much about the past words intersections there, so much as the future words ones.
Well, I mean, it kind of depends. Like, for instance,
it could have rained consistently with what I see now. Like we're at X there.
Yeah.
We know that it didn't actually rain yesterday, but in some possible
Yeah.
timelines consistent with this moment right now, it rained yesterday.
Yes.
Okay.
Yeah, exactly. Like, say this is the special one, the one that we think happened,
Okay.
but we say, yeah, it could have rained yesterday. Yeah. I think it's worth contrasting that with yeah, something else I wanted to bring up is counterfactuals. So you can say a whole lot of stuff with tense and modal operators. One example I like, or I use in the paper, is we imagine black and white playing chess, and then whatever, black blunders his bishop, plays on and ends up winning, but then nevertheless laments the fact that could have won much sooner, right? Okay, so what's going on there, and it's something I kind of want to highlight as like potentially, okay, so here's the actual one we're in, and let's say here's the win state. You know, he wins here, but nevertheless laments his loss. So says something like, well, it's possible that in the past, win, right? What does that mean? Well, it means there's some other game, here's say sigma, where in the past win. This is a little bit strange because we're outside, because there are no games of chess where you've won, you know, there's like, here's the end of the game over here where you actually win, right? And so these times are kind of like outside the actual domain, but that doesn't mean they're not times. So we still are quantifying over all y. So we can still evaluate times inside the domain. So let's say, you know, the domain begins here. Say this one begins here, let's say, and they start at the same, let's say, over here, something like that. So what am I saying? I'm saying, well, go backwards. Here's the winning state there. Okay, so that's kind of what we're allowed to say inside this language. It is very common. I mean, this is a little bit awkward to say. It's possible that in the past I won. I mean, we can understand that, but it's more natural to say I could have. If I hadn't blundered my bishop, I would have, or I could have won, right? So how would we do that? We'd say, in the past, say not blundered bishop, and let's be strong about it. I would have won, say, won, I don't know. So far, this semantics does not have the resources to interpret this. And the reason is because counterfactuals, at least the way that I want to model them, really speaks about what goes on inside a world state. So let's draw them now as these kind of things that have structure, mereological structure, a whole bunch of states all fused together. And yeah, these world states are these maximal possible fusions of states. And then what a world history is some evolution thereof. And it's very typical to think, okay, say we're over here. We say, if I had gone, you know, if I hadn't blundered my bishop, what am I saying? It's like, okay, there's a past time, go back there, think about the other evolutions where it's very similar to this one, except I didn't blunder my bishop. Well, how do we do that? We think, okay, well, here's all the other moves. Maybe there is one key move. Okay, change this board state such that I made that move instead. And look at how it evolves. And of course, it could evolve different ways. But look at those evolutions. There's a winning state, which happened somewhat sooner than my winning state here, right? And so to do that adequately, I feel, we need to be able to talk about the parts of these world states. But for my purposes here, just for tens and modal operators, we don't need to do that. We can take them to be primitive for the time being. Yep.
I think people here are interested in temporal logic as like a specification language for maybe a design of something. And the common ones that we've seen are like LTL and CTL. How do you, can you help us compare this as like an alternative of the same sort of thing as those, but with some sort of different, I guess, computational benefit? Or
Yeah.
Question, what are LTL and CTL?
Yeah, like computation tree logic and linear temporal logic.
Okay, got it.
Yeah.
Yeah. So there's a past hope that I had to somehow fit in a systematic comparison of all those frameworks. I guess I feel like the difference that I see is that I'm helping myself to a bit more, yeah, I'm starting off with kind of more resources. And so I expect to be able to express similar things. I guess that doesn't, to me, that seems like a virtue to both, that if there's some kind of translation between these different ways of thinking. It's not to say that this is necessarily needed for all of those applications, especially when you're thinking about, say, like linear tense logic. Then it's kind of like, no, it's okay to be talking about when a thing happens. You don't need to, you're not trying to reason about the different states of the system. You're trying to reason about what is true at what times, and you're trying to be, so it's kind of good actually to pare down to just the primitive structure that you need in order to do that systematically. So I think when it comes to applications, there may be some very clear advantages to a system that has fewer primitives, the definitions are simpler, and it gets you what you want. I guess the advantages maybe, which, yeah, I'd like to explore, are when, no, it actually would be nice to have a little more expressive power, and that, you know, especially for kind of, I mean, yeah, where I guess the applications I'm thinking about is, yeah, I guess I don't have like a clear example where it's like, aha, you need exactly my frame, you know. I actually feel like I trust these systems to have been developed around the applications they have to have most of what they need. And that especially when there are applications, you can go and check that you're getting what you need. So I guess if anything, you know, assuming that's true, assuming that these systems are kind of adequate for the applications they're intended for on their own, then the most this could provide is some kind of unification, I guess. But sometimes the unification is cheap because it's like, you know, if you have something that's purpose-driven and, you know, built to task, well, that's better than some unification in which you have to then define away the thing that you were trying to get, right? So, but yeah, I do hope to develop those connections. And yeah, I don't have,
Time check.
Oh, yeah.
Probably have like 4 minutes left.
oh, sure, yeah. Yeah.
Let me review a little bit of history. Centuries ago, not quite, but Lewis and Langford introduced modal logic properties
Mm-hmm.
and axiomatized certain kind of modal operators. S4 is a particularly nice one. Gödel then realized that S4 gives an interpretation of intuitionistic logic
Mm-hmm.
there. And so we can think of those properties to help us in giving formal proofs in the logic of those. Now, in his early days, Tarski wrote a lot about Boolean algebras, axiomatization for Boolean algebras, and the theory of truth. He would have proved the representation theorem for Boolean algebras, but Marshall Stone got there quicker because Marshall Stone did functional analysis and had thought in terms of things like ultrafilters from functional analysis, and so then he then put 2 and 2 together and realized that gives the representation for Boolean algebras. But then Tarski and McKinsey together in the early days when Tarski just came to the United States with JCC McKinsey, they thought about Boolean algebras with operators, and so Tarski and McKinsey extended a representation theorem for Boolean algebras with an operator like the S4 things, and so they saw that it could be representation theorem could be gotten by using alternative relations that are symmetric and transitive to give S4. Tarski and McKinsey had Kripke models before Kripke did, but Kripke was only a teenager and he thought of them on his own, but he made the story more philosophical, so people credit Kripke
Yeah.
more than Tarski and McKinsey, but they really had it before.
Oh, that's great to
They
know.
had it
Yeah.
before Kripke did. But now, later on, because you can think of many kinds of Boolean algebras, complete Boolean algebras, there was a lot of question that Tarski had about infiniteistic logic and complete Boolean algebras. But then Solovey realized when Cohen was doing the independence proofs that he could reinterpret Cohen in terms of I'm blocking for a minute. In terms of Boolean valued logic, I mean, Cohen built up models that violated the continuum hypothesis, but Solovey realized that you could think of it as giving a Boolean value in a certain very large complete Boolean algebra. And then Solovey and I wrote up things about doing models for Zermelo-Fraenkel set theory over a large complete Boolean algebra. So what I'm asking you is, wouldn't you rather, after all your analysis here, think of what the logic is, the formal logic is for your modal things, and then think about what will happen if I take a complete Boolean algebra with modal and tense operators. I could then build up a model for Zermelo-Fraenkel set theory with tense operators. Shouldn't you tell us what your formal logic is? You're motivating this, the formal logic, but tell us what the formal logic is. Yes?
Right. I don't know that I actually scrolled all the way down.
So there are properties like S4. So what you have on the left-hand side
Yeah.
is S4.
Yeah, that's right. And
Now you have some properties,
I have some tense properties.
some tense properties. Yeah.
That's right. And some, yeah, exactly, some distribution laws and so on. And I don't, the truth is, I mean, okay, I've checked that all of these are valid, but what I don't have is anywhere close to a completeness proof. But I don't feel like it should be too difficult, because I guess I feel like the quantities are all independently well studied, and there's a lot of resources to use. So that's something I've
Well, see, maybe
aspired to.
You could do it backwards.
Mm-hmm.
If you take a Boolean algebra with these operators there, what is the representation theorem that corresponds to what Stone, Tarski, McKinsey did for representation of Boolean algebra with operators?
Yeah, yeah.
You could also, I hate to tell you, think of intuitionistic logic with operators too, if you wanted to, but
Yeah.
Let's stick with Boolean. So, from these axioms, can you now give a nice representation theorem for a Boolean algebra with operators like that?
Not yet, but I definitely agree that that would be a nice thing to have.
Yeah.
Okay, well, why don't we take this one to thank the speaker?
Oh, cheers.